Our last concept in this section is a fairly simple idea, but it's extremely important because it forms the theoretical foundation for a lot of what we do starting in Chapter 5. And we're going to state this in what we call the unusual event principle, which says if we make an assumption or a claim about a random experiment and then observe an event with a very small probability based on that event, called an unusual event, then we conclude that the assumption is most likely incorrect. Okay? So we start off with an assumption about something, and then we go out and we observe something in the real world, and if that observation has a very small probability based on the assumption, then that's an indication that our assumption is probably incorrect. Now, the next thing we might ask ourselves is, well, just what do we mean by a very small probability? Well, we're going to state that here in the unusual event guideline, which says that if x is binomial and represents the number of successes in a random experiment, then an observed event consisting of exactly x successes is considered unusual if one of these two inequalities is true. So the probability that capital X is less than or equal to x is less than 0.05, or the probability that x is greater than or equal to little x is less than 0.05. Okay? So we need to calculate either this probability or this probability. If either one of those is less than 0.05, then we consider that event to be unusual. Now you may ask yourselves, where does that number 0.05 come from? And there's nothing magical about that number. It's just a number that's commonly used, and we're going to see this number come up a lot throughout the rest of the semester. So let's apply this to an example to illustrate what this all means. Suppose a university student body consists of 70% females. To discuss ways of improving dormitory policies, the president selects a panel of 15 students. He claims to have randomly selected the students. However, one administrator questions this claim because there are only 5 females on the panel. Use the rare event principle to test the claim of randomness. Okay? So let's look at what's going on here. We got 70% female. So that means that if we were to select 15 students at random, then about 70% of them should be female. Well, that's what, about 10 students that should be female. But we didn't get 10 students. We got a lot fewer. And so that's an indication that maybe these students weren't randomly selected. And so there seems to be some validity to questioning the claim, but we want to test it a little more formally. Okay? So first of all, let's define our random variable. Let's let x equal the number of females on the panel of 15. Okay? We define this random variable because that's what we're interested in, the number of females on this panel. Okay? Now, if the students really were randomly selected, then x would be approximately binomial of 15 trials with a probability of success of 0.7. In this case, the success is getting a female. If randomly selected, that probability should be 0.7. We have 15 trials, so x is binomial. And so the observed number of successes was 5. That seems a lot smaller than it probably should be, and so we're going to calculate the probability that x is less than or equal to 5. Well, x less than or equal to 5 means x equals 0, or 1, or 2, or all the way up to 5. And so we need to calculate those probabilities by plugging in the values of our parameters. N is 15, p is 0.7, to our PMF. Then the probability that x equals 0, 1, 2, or 3 is very small, practically 0, and so that's where we get these numbers here. Those probabilities are technically not 0, but they're so close to 0 we'll call them 0. This is the probability that x equals 4, the probability that x equals 5. If we add those up, we get 0.0036, and that is much less than 0.05. So because that probability is so small, we would our conclusion would be to reject the claim of randomness. Okay? Now that doesn't prove that students were not randomly selected. It's just enough statistical evidence to reject this claim of randomness.